In this presentation we will continue the discussion on how to represent the system's vibration properties in system characteristic functions. So we will focus now on the impulse response function. So how can we obtain the impulse response function from the system characteristic function? And more important, how can we use the impulse response function to describe vibration characteristics of a system like this, for instance. So if I hit here, you hear a decaying tone at a certain frequency. So how can we obtain from the impulse response function the decay time, the resonance frequency, the vibration pattern, and so on from this impulse response? That will be the topic of this presentation. So let us continue our discussion on system characteristic functions. Last presentation we stopped when we have reached the system transfer function on pole residue form. Now, so we stopped at this point where we showed that the system transfer function for a vibrating multiple degree of freedom system can be written in this form as sums of complex conjugate pairs of ratios like this. Now it will turn out to be fruitful then to continue this discussion by converting this to an impulse response function. So to do this we need to inverse Laplace transform this expression to the time domain. So by doing this we reach this, by using the inverse Laplace transform of this kind of expression, we get this impulse response contribution. So the residue multiplies the exponential of S1t. So the poles appear as exponents and the residues appears as multiplying factors. And then of course we have this complex conjugate term that adds to the original one here. So if we make use now of this complex conjugate terms here, we can sum these and obtain 2 times the real part of each term here, or each pair of terms here rather. The function u here is simply the Heaviside function. So if we consider now the fact that both the pole and the residue must be complex valued, then we can express the pole as a real part plus I times imaginary part, beta. And we can express the residue in polar form like this, the magnitude, the absolute value, times the exponential raised to the imaginary unit times the phase angle phi. So if we introduce now this into the expression for the impulse response function, we get this expression. So first of all we have the real part of the complex exponential with argument beta t plus the phase angle. And then outside the real part as a multiplicative coefficient we have 2 exponential alpha t, t for time, and the absolute value of the residue, the magnitude of the residue. So this real part of the complex exponential here, of course, by using Euler's formula, we can find that this is actually the cosine of the same argument. So we reach in the end this expression for the impulse response function. This factor here is the amplitude, and this determines the oscillation. So the free vibration angular frequency is determined by this beta, that is the imaginary part of the pole. The amplitude's time dependence, since alpha is always negative, it turns out to be a free vibration decay. So this alpha determines, that is the real part of the pole, determines the decay time, the free vibration decay. And then if you consider the full factor of cosine here, it will give you the free vibration amplitude. And finally, this phase angle will give you the direction of the displacement of the impulse response. So for instance, if we now have two observation points with different magnitudes of the residue and different phase angles of the residue. Let's say the first point has phase 0 and the second point has a residue with phase pi. Then the magnitudes will give us the relative amplitude of vibration in the 2 points, and the phase angle will tell us the relative direction of vibration. If there is pi radians difference in phase, then we know that they vibrate in opposite phase, in opposite directions. So, a graphic interpretation now. If you now plot this impulse response function, it will look something like this. The starting amplitude will be 2 times the magnitude of the residue. And then as you see, it will be decaying slowly, and you have a certain oscillation rate. The oscillation rate, or the period of oscillation, will be given by 2 pi over the imaginary part of the pole. So that means that the oscillation frequency in hertz will be given by beta over 2 pi. Then the decaying amplitude here will be given by the logarithmic decay, exponential, the exponential of alpha t, where t is time. So to summarize this now, the Laurent series expansion of the system transfer functions will give us a set of poles and residues, and these will appear in pairs. So to each pole Sn corresponds a residue Rn. Moreover, the poles and residues will be either real valued or complex valued, and they can be shown to be pairwise complex conjugates, the poles and residues. And it's the complex conjugates that are of lots of importance in vibration. So the poles gives us information on the free vibration frequency and decay. So the free vibration frequency, that is actually, as we will see later on, frequencies where the amplification is large, that is where the system is sensitive to excitation. So if we have an excitation acting with a frequency close to this free vibration frequency, then we will get resonance. And the decay rate is of course as a measure of the system losses. The residues, on the other hand, gives us information on how the observation points vibrate, their amplitude and their phase. So by comparing different observation points, residues, we can get a picture on how they, on the relative vibration between the points. So that means that if we calculate the impulse response for a set of observation points that is distributed over the system that we investigate, then we can get the relative vibration patterns at these poles, that is at the system sensitive frequencies, the resonance frequencies. And that is actually then the system's vibration modes. And these are the properties that we are looking for in this course. So what I'm trying to tell here is that the pole-residue form of the system transfer function is one very, very fruitful way to look upon the system transfer function. In fact, it will turn out that later on, when we want to determine the vibration modes, the mode parameters from measured data, then this system pole representation is what we are going to use. So, remember now the example from the previous presentation, the bicycle model of a car. If we continue this numerical example, we obtain for pole 1, S1, that was equal to this complex number. And in fact, it turns out that this pole is, well, appears both for all four transfer functions that we can determine. And the residue for corresponding to the pole 1 for the system transfer function coupling force, exciting force with the rotational degree of freedom is this. And the corresponding residue for the other transfer function corresponding to exciting force and the translational degree of freedom is this. And as we said before, beta, that is the imaginary part of the pole, can be converted or can be the basis of estimation of the resonance frequency for this mode. You simply divide the imaginary part with 2 pi, and in this case the result will be roughly 1.1 Hertz. The real part of the pole will give you the amplitude decay. So this value here, this value will give you the decay rate of the vibration when the vibration source is removed. Now the residues, this value and this value, will give you the mode shape vector. That is actually the relative amplitudes of the motion quantities that we measure. In this case, you can see that the first, in this case it's the rotation angle, is larger, a factor, say 6 larger, no, not 6, let's say a factor 5 larger than the translational degree of freedom. And they have the same phase, so they move in phase. So if we summarize them, for the first pole, the first mode, we obtain the first mode, vibration mode. And the system pole for this is equal to this, as we saw before, and the mode shape vector is this. And if we do the same thing then for the second pole, we can find the modal properties of mode 2. So the second pole, second system pole is this, and the mode shape vector is this. And now you can see that we have a minus sign at the second component here. And that means that the translation and rotation are in opposite phase now for this mode. So if we plot these, we can see the mode 1. If we plot the impulse response functions, you see the motion here is in phase, and we have the, well, actually here it's wrong. This should be the rotation, because that was larger in this case, and the green curve should be the rotation. And for mode 2, we a similar way, but now this green curve should be the translation and the blue curve should be the rotation. So note now that these are misplaced. So here should be translation and here should be rotation. And as I said before, they are in opposite phase. They have different signs. So, in experimental modal analysis, which we are dealing with in the larger part of this course, our task is actually to find the modal model from measured system properties. That is, we have to find the system poles and mode shapes for the system that we investigate. And we will use frequency response functions or measured impulse response functions. So we will actually measure frequency response functions or impulse response functions and determine the system poles and mode shapes from these measured data. That is the basic task in experimental modal analysis.